Well, I'd like to thank Mara for that great leading question, because this presentation is going to focus on the ontological aspects themselves. And I also like to thank the CGI for having us speak here. The presentation on ontology and geoscience is a research effort right now, not a standards effort, and not a CGI activity, but something closely related to the CGI activities that we've spoken about thus far. That said, this is motivated by a project across North America, Australia, and Europe looking at improved 3D modeling. And a package or a part of that activity is the recognition that modeling requires a lot of geological knowledge, and that knowledge needs to be managed in some way. And part of the management of that knowledge is a structure for it. The intuition is that 3D modeling, it has underutilized geoscience knowledge thus far, focused primarily on data, and that there's an opportunity to enhance the amount of knowledge involved. So that is the overall use case that we're working within that project. But within this work, we're looking at how to structure geoscience knowledge in general. But the focus in the 3D modeling ontology, which we might call textbook knowledge, or interpretations as opposed to, for instance, data. Although from an ontological point of view, being able to represent any aspect of geology is really the focus here. So as many of you know, knowledge management is really a hot topic these days, stimulated by large technology companies. For example, Google published a knowledge graph in 2016 with billions of facts and hundreds of millions of objects to help search engines navigate the web. Underlying that is a ontological schema, an ontology called schema.org, which helps all that work. So knowledge management effectively does require some structure for the knowledge in order to effectively use it, etc. So as we move from looking at markup languages to a more ontological structure for usage, it indicates the need for a broader development called an ontology. So we've unimaginatively named and experimenting with geoscience ontology. And it basically consists of a hierarchical structure of entities, from the most general that can apply across any domain called common, to those that are general to geology, to those that are more specific details. We can roughly map these onto the GeoSciML in the sense that GeoSciML schema would be more like the geological layer, and then the vocabularies, which are the details and which can change from one implementation to another, for example, or from one system to another, possibly on more of the modules. And then on top of that, there's of course a language that these can be encoded in this case OWL, to take the fundamental concepts and map them. So that's the overall framework that we've been working in. And I should say that this work's been ongoing for around 4 years now, if not more, although initially started more than 15 years ago and paused for a little bit. So it's been an ongoing research effort for a number of years. Its predecessors are in N80M, which I co-chaired, GeoSciML, which I initially co-chaired too, and then a ontological implementation of many of these concepts in an effort called Dolce Rocks from the early 2000s. All this work has now been wrapped up and made progressed under the GSO umbrella, and it's roughly aligned with other more current and recent ontological directions that you can see listed here below. The differences being either in terms of breadth or depth of the concepts covered, or the particular ontological interpretation of some of those concepts. I'll get into that a little bit as we go along. Particularly with respect to efforts in this group, it's most related to GeoSciML, and that's a question that often comes up. So I would have to explain the difference and how it fits into the GeoSciML environment as, on the one hand, providing a formalized conceptual schema for GeoSciML. Currently, GeoSciML has an informal conceptual schema, which is the NADM model. But secondly, because in terms of the ontological technology, there's also an encoding of those data that provides a language whereby instances of those concepts can be expressed. So it also provides a language for expressing both data and meanings of concepts in a formal way. And so it relates to GeoSciML both conceptually, expands somewhat beyond it, reinterprets some of the concepts, but also allows an alternative encoding as well. The development for this required it to be both broad and deep, so it's meant to cover any type of entity in geology, so have a place, a framework in which that can be plugged in, but also to be modular in that under that general framework, individuals can focus on particular areas and still plug it into the basic framework, or even have alternative interpretations of various geological entities for particular systems or uses. But importantly, also, it was meant to be standalone, to be used, without necessarily a lot of imports for both compactness, but also consistency, as we were trying to deal with a very broad range of things. Consistency became an issue in order not to have logical inconsistencies. And so we decided to, for the time being, to avoid imports where possible. There's a much detailed technical discussion around that, but we won't get into that now. Methodologically, it was generated by looking at existing efforts in upper ontologies and in geological ontologies, encoding as UML diagrams and some first order logic, using tools such as TopGrade and Protege to generate the OWL representation, and then going through many examples of testing, and in the process now of implementing within some kind of more knowledge management systems, such as using triple stores and graph databases, and moving towards integration with the new 3D model encoding, the Loop project. But we're really still in a testing phase because of it's such a large endeavor. There's a lot to be sorted out, and I'll talk about that a little in a second. But to give you an example of the type of organization that's been evolving over the last 4 years, the common entities are things that really refer to upper ontology. So these are fundamental categories and concepts that can apply across any domain, such as space, time, events, qualities, processes, etc. Initially, we started off using one of those called Dolce, but then over time, shortcomings became realized, and the end result is rather a challenging effort and somewhat a dangerous effort, and that is trying to merge the different aspects from various of these upper ontologies. So, for example, space and time and other aspects from VFO, qualities from Dolce, roles from UFO, and so on. The geological layer builds on the previous work, as I mentioned, in NADM, GeoSciML, and Dolce rocks primarily, but making significant ontological interpretations of things. And the modules are things such as different organizations of rock types or settings or types of geological properties, for example, that can be exchanged and extended as required. To give a sense of the scale of the effort, the common layer contains around 100 classes, the geology layer are close to 150, whereas the modules contain close to 7,000 classes and over 120,000 axioms in the logical encoding. Given the size of this and the scope of the effort, we're still unraveling various inconsistencies that are arising. So although there is a version 1 published, we understand that there are issues, both in terms of conceptualization, but also in terms of some logical consistency that we're still sorting out. But there are close to right now 30 modules in place, largely based on the GeoSciML vocabularies, but also others. To give a flavor of some of the analysis, just talk about these objects quickly, various distinctions being made. So a core distinction is the notion of a geological object. And a particular distinction here is between objects that are specific in geological units, where the distinction really comes down to context. So for instance, specific objects are not contextually dependent on anything around them. So for instance, a boulder or a particular fossil might be moved from its environment and placed somewhere else, even another planet, and they'd still retain identity. They'd still be the same boulder or fossil, whereas something like a geological unit, typically, if it's context dependent, like a stratigraphic unit, cannot be moved from its surroundings and be the same unit, because the surrounding rocks would be the same, the processes used to develop it would be different if it was in a different place, like on a different planet. So context dependency is a primary distinction here as part of the ontological analysis, for example. If we move on to other types of analysis, then geological structures, for example, are analyzed as things that are dependent on multiple entities, one of which is a rock body at least, or one or more rock bodies and other parts. So for example, something like a contact or a fault is hosted by multiple rock bodies, but also consists of a particular surface that exists between those rock bodies. If the fault or if the rock bodies move, that's a different surface, but different rock bodies would result in a different fault or contact, for example. So there's some intricate dependencies at play here that have been analyzed and in fact have led to a whole new theory of features that's in progress and in progress published right now. Geologic time is also an interesting analysis because it turned out that there are also these multiple dependent features. A geological time unit, for example, is highly dependent on the rock record, as we know, but this is a dependency, and it's a relationship between a rock record and a particular chunk of time. So if one changes the rock record, one ends up with a different geological time unit, even though it may refer to the same chunk of time. And implications of that, of course, is that a time scale for another planet like Mars and one on Earth are very different because of different rock records, which we know intuitively, but we need to formalize in terms of the type of dependencies that are in process there. So that's part of the analysis that went into the geologic time framework. And of course, an ontology can't be complete without relations. So fundamental relations for space and time in geology, with an intuition that geological relations are combinations of spatial and temporal relations, particular combinations of them, so that they reflect what we understand in terms of the distribution of entities in space and time geologically. There's a number of those, but this is really a very early effort and very incomplete. Just some of the ideas, but they really haven't been worked through yet fully. But you can see that there are a few geological relations there sketched out. I won't go through a lot of examples, but just to give a flavor of what this might look like in action. So if we take, for instance, this structure, this stratigraphy in front of you here on the screen, and focus on the green unit, which is a Jurassic formation. It has an encoded on the right here as two parts, the two green parts, an upper and a lower portions with a boundary at the top and another boundary at the bottom, and a thickness value associated with it that ranges from thin to medium, for example. Similarly, the encoding of timescales takes into account those dependencies we discussed earlier, but is very aligned with the approaches done, for example, in the time ontology that Simon's been working on and others, but incorporating some of that more ontological analysis of dependencies. So, for example, the lower Jurassic here has is part of different time scales. It has parts themselves that are smaller units and has previous and next intervals. And then the 2017 base boundary of that, for example, has a time point as an essential part with a particular value associated with it. And we can continue this line of expression with geological events, as well as geological structures. I won't go into the details here, but there's a nice syntactic encoding in the OWL format that follows the ontology through these various examples. And if we then store these in semantic databases, whether they're graph databases, triple stores, etc., then can take advantage of ontological query languages to be able to extract information from them, either on the web or on the desktop, such as and generate standard tabular information, for example, from the ontology, such as the constituents, roles played by a unit, proportion, etc. On the screen here from an example provided by the British Geological Survey and Rachel. Many thanks. So to wrap up, the effort we've just discussed is publicly available for commentary. As I mentioned, it's an ongoing research effort. It's not a standard or a standardization effort at this point, largely because I think we're not really yet there with standards for this area. There's still a lot to be understood. And this is one effort to try and understand some of those things better. As I mentioned earlier, there are other efforts also. But there is a published reference document at the DOI here from the Geological Survey of Canada. There's a public release one of the module and a GitHub where the ongoing work is also happening, available. We are in the process of, as I mentioned, debugging some of the consistencies we're finding. The issue is that it's such a large ontology that not all the reasoners and consistency checkers can work on the whole thing. And so we're trying to run multiple types of consistency checkers over it, and they all pick up some things and not other things. In some cases, they're clean. So we're in the process of that, as well as trying to apply it to real data and work out the actual knowledge manager component within semantic databases to link them to 3D modeling codes. And with that, I think I'll wrap up. Thank you for attention, and thank you to the CGI for allowing us to present this related work. And I'll open it up to comments or questions.
Thank you, Boyan. Discussion, please. Very positive feedback in the chat. Simon Cox, thank you. Temporal relations completed here. So Simon, thank you for that link in the chat regarding temporal relations. Yeah, very positive feedback in the chat. Questions, comments, please, in the chat, or go ahead and unmute, please.
As I mentioned, it's early days, and there's a lot to unravel here. We'll appreciate any comments or feedback.
All right, a question from Ursula. Boyan, do you try to keep stratigraphic terms up to date in agreement with the ISC?
Generally speaking, we have expressions of various time charts. So up to almost the latest, I believe. Steve can jump in there. He's the one that's been doing a lot of that. So in terms of the time charts, yes. In terms of the concepts, also yes, although our analysis has led to some more general, higher level concepts that we're using as a framework also. Steve, did you want to add to that?
I was just saying the way we've implemented the time scale is that there are versions, and right now we have the 2004 version, the 2017 version, and the 2020 version are implemented. And it's rigged up. We could add the other ones, but didn't go to that level of detail in the implementation.
An interesting ontological problem, though, for example, is what is the relationship between, for instance, Jurassic in each of those versions and Jurassic overall? So what is the note, how do you deal with the general concept of Jurassic and the particular concept of Jurassic in any one timescale, because it's referring to each one refers probably to a different aspect of the rock record. So they have a different dependency. We have an initial interpretation of that, but I think there's still a lot that could be done there. So it's a very tricky question, that one.
Very good. Oh, all right. So thank you, Boyan, and thank you everyone for good discussion. And there are more questions in the chat. So Boyan, perhaps you'll be able to respond to at least some of those, but I thank you all for discussion. And now let's go ahead to you, Zank.